right. Hi, Reed. You're all here. All right. I'm going to turn this just a little bit more. Whoops. Good enough. All right. So, you guys all have your letters that you wrote?
I have mine at home. Like you left your 7 somewhere. I had my one. I just wrote it.
All right. Yep. All right. Very good. Here, let me see what you got. Yeah.
Here's the page.
Yes.
Yeah. We didn't finish it. Yeah, I know.
All right. So, okay. So we are going to continue where we left off last week. I think we were in the activity manual on 139. 139. All right. All right. So we did first 4. Is that right?
Yeah, we're going on 5 and then the rest.
We're on 5. All right.
Okay, 139.
So, if you want to use your books, you can be looking at, this is on pages 212 to 219. Pretty good. All right, so number 5, Newton's second law of motion says that an increase or decrease in force is related to an increase or decrease in
force?
No, force isn't the answer. So it's the
motion.
2 blanks there.
Oh, acceleration.
Acceleration is one of them, and the other one is
Mass.
Mass. Yes, good. So the wording of this is might be a little tricky for you guys because usually we read this the opposite way, but it means the same thing both ways. So Newton's second law of motion says an increase or decrease in force. So if there's less or more force, it's directly related to more or less mass and or acceleration. Does that make sense?
Is that the formula? The mass?
Yeah.
Mass times.
Mm-hmm.
Yeah, and so guys,
Yeah,
it's
wrote it the opposite way.
Acceleration.
what number are we doing?
Number 5.
Oh, we just did 5.
Okay, which is mass times acceleration. So on number 5, second law of motion, an increase or decrease in force is related to an increase or decrease in acceleration over mass.
Mm-hmm.
Yeah, well, because I always try to give them a number equation. So like 2 times 5 equals 10. If we instead of doing 2 times 5, we did 1 times 5. Wouldn't that be less than 10? If we decrease the first number, it's going to decrease the answer.
I know
it's going to
6.
decrease the product. And if I decrease the second number, instead of 2 times 5, I do 2 times 3. Is that going to be less than 10?
Yeah.
So that's why I do it.
Yeah.
Just so they have a concrete.
Isabel?
6 is force equals mass times acceleration.
Oh, very good. Yep. So you have the formula right there.
It gives the big hint because of in the book and in the thing it actually puts an F after the force.
Oh, right. Yep. Very good.
They do what they do. MA equals F.
Yeah, look at.
It's F equals M times A.
Right.
Yep. Yes. Very good.
You're gonna have more force if the object has more mass, or you're gonna have more force if the object is going faster.
Yeah.
Think about trying to stop. Think about the damage a big truck can cause that's going with 60 miles an hour. You don't want to get hit by one of those.
Yeah.
When I was learning to drive, my brother always told me, don't mess with the trucks.
Yeah.
Because one time my mom was messing with a truck, and the car my dad drives now, she was driving, and then she went to swerve over, and then the car flipped upside
Oh
down.
my goodness.
Oh wow.
That's
And
awful.
Did it break?
No, it broke, but wearing a seatbelt saved my life.
Yeah.
Wow.
Oh, I
Yeah.
want to touch
Because
that
she
one.
could have gotten a really bad concussion,
Mm.
and there's still dents in my daddy's car.
Oh wow.
Well, it's my mommy's car, but now it's my daddy's car.
Gotcha. Well, that was one of my husband, over the course of our relationship, has had a couple of motorcycles. He likes to buy and trade vehicles like most people do. I don't know. Well, teenagers
Baseball
do
cards.
baseball cards back in the day.
Yeah.
And one of the, he always, he has the final say, but he likes to ask me my opinion just to be nice, kind of thing. And so anytime he asks me, my rule is I don't care if you have a motorcycle, as long as you're not driving it on the throughway.
Oh, yeah.
Because that's where, at least I've seen most of the time people
Yeah.
die on motorcycles is on the throughway. And
Yeah, the
When
problem is
we
with the
were-
motorcycle,
we
there's
were
no
camping.
margin for error. If you do have an accident,
Yeah.
you have no protection.
yeah, especially
Except for a
when you're
helmet.
going. Well, yeah, when you're going 75 miles an hour,
Yeah.
body meets the road.
That's
One time I went to
good.
the Blackthorn
Where's the
and
baby?
it was like
Can I
a
take
motorcycle week.
Yes.
I had an electric motorcycle. It looked so cool. It was like I don't know, it just looked good.
All right, so let's try to get
let's get through it.
through these before we start. Do you have a question or you want to tell a story? All right, so let's try to get through this before we, so we can make sure that we get all of this done.
Okay.
Okay, so for part B, oh wait, no, we have to do number 7 first. So number 7, Newton's third law of motion says that for every force exerted, there is an equal force exerted back. The law of blank and blank. Anybody remember what those are?
Law of mass.
So it was saying
Momentum.
for every force exerted, there is an equal force exerted back. So for every
Motion.
action, there's an equal and opposite
Reaction.
reaction. Very good.
Action and reaction.
Yep.
Every,
So it's summarized that the law of action and reaction.
yeah, every time there's a force exerted, there's going to be some result of that.
Mm-hmm.
It's going to cause
I got these
something else to happen.
Nice. Very cute. All right, so let's go on to part B. Everybody got number 7?
Mm-hmm.
All right, so for part B,
This is going to be the law. Action is the first erase the error.
And I got
You put the action and reaction. She only had one blank for that.
oh, okay. All right, so for these, we're going to look at some examples, and we have to determine which law of motion it's referring to. All right, so these might be a little bit tricky because I know they all have similarities, but we can learn to distinguish between them. So number 8 says you are riding a skateboard. You fly forward off the board when you hit a curb.
Second law.
So the second law of motion, and maybe we can summarize them up here on the board so we can remember. So the first law of motion says that an object in motion tends to stay in motion until it is acted upon by another force.
That's one.
Right, very good. So that would be the first one. Objects in motion tend to stay in motion And that's not the whole law, I'm just summarizing it there, but you get the idea. And the opposite is true. Objects at rest tend to stay at rest, right? Unless they're acted upon by another force, like somebody kicking it or something.
Now, is that where the word inertia comes in? Is that inertia?
Yes, although I think
That's not part of
inertia is more
The resistance to a change.
related to, I think they relate that one more to the second law.
Okay, it's under the first law here on page
Oh, it
216
is.
on 216.
Yes. Yep. Yeah, so it would be a resistance to change in motion.
Right.
Okay. So the second law of motion is that law, force equals mass times acceleration. So I'm just going to summarize these up here just so we have them in front of us.
Yeah, right here. They're gonna have to take it home. You're gonna forget.
Wait, why are you doing it backwards?
Now you're organized. All you have to do is put it in there.
Because it's mass times force.
Okay, now number 2.
No, it is.
No, force equals mass times acceleration.
But in the book, it's like that. It goes mass times.
Oh, I just wrote it the opposite way. It still means the same thing.
Is this for number 9?
No.
Oh, I was just summarizing the
the
laws
laws.
up on the board,
The
so
laws,
we
okay.
could refer back to them. And then 3 is action and reaction.
Okay.
Just so as we're going through these, you guys can kind of.
Yeah, well, there they are.
reference.
That's a good thing to know right there. Yeah,
All right.
yeah. Not here to be blocked out. She's out standing in front of reading.
Oh. All right. So number 9. Number 9 says the red bumper car at the fair bumps your car into the green bumper car. The red bumper car goes backward as your car goes forward. Azalea?
So,
What law of motion is
2.
it?
3.
That one would be 3, so it's action and reaction.
Yeah, one car
Right.
bumps into another one, and that makes something else happen.
Yeah.
And that's good.
All right.
It's third.
We got that one.
Got that pencil in there?
All right. So number
you got
10.
I think so.
Number 10. A coffee cup is filled to the rim. The car accelerates forward, and the coffee spills in your lap. Gavin?
Force equals mass times acceleration. Oh, action and reaction. That means 3. 1, 2, 3. 3.
So, anybody else have a different idea? Isabel?
1.
1. Can you explain why?
Because if your cup is moving forward, it says accelerates.
Mm-hmm. Mm-hmm. So we could assume that had the car stayed at the same speed, so that would be the opposite of this. Objects at rest tend to stay at rest unless they're acted upon by another force. So really, to summarize both of those things, you could say that, and I think this is actually the way they have it worded in the book, is that an object tends to stay at the same velocity unless another force acts on it. All right. Gavin, you understand that one?
I think so.
All right. All right, so
Well,
let's...
seatbelts, yeah, right? But you'd still be traveling at that speed when the car abruptly stopped.
Mhm.
We need the seatbelt to keep us inside the car.
Yeah. All right, and here's one we looked at with the example that we talked about quite a few times. Number 11, the batter swings the bat hard, sending the ball into the seats for a home run.
Right into the seats.
Into the stands, like the seats that are around the ball field. Azalea?
2.
2. Yes, very good. All right. Pretty good.
If Sarah was there, she would be taking notes.
Oh, well, you can take notes if you want.
No,
It's always good to take notes. Helps you to remember, and then you have something to study from later.
it's sort of hard to take notes. Because then your hand gets cramped and then you have to
One
start
thing that
writing
would be
fast.
good to copy
I
down is
understand.
what Mrs. LePage put on that whiteboard, because that helps you remember what each of those 3 laws say.
Yeah.
You know, that would be worth. If I had to learn this, I would have written down what was on that whiteboard right now.
Actually, probably would be a good practice for you guys is if you had a notebook open when we're in class. And then if I say something that you want to remember or you think you might have trouble remembering, you can always write it down. And then you have it to look back on.
Yeah.
All right. Well, let's go on to number
12.
12. All right. Dad lights fireworks with a match. A firecracker explodes and shoots into the air, displaying many colors. Azalea?
3.
3. Very good.
That's a big reaction.
Yes. Yeah. I think actually once the weather warms up, we have a very exciting little lab that we're going to do. But we have to do it outside. Well, it's actually for my chemistry class, but I'm thinking if I can coordinate it at a time that's okay for my other classes' teachers at the time, that if all of you got to observe it, it would be pretty exciting. I don't know yet. We have to see, probably in a few weeks when the weather warms up
What
a little
is it?
bit, because it actually causes a pretty big explosion.
Oh,
So we would have to do it outside.
Wait,
Yes, we'll
is it
definitely
elephant-
videotape
Is
it.
it elephant toothpaste?
No, it's called Purple Sugar Fire.
it'll probably, if it happens, we can do it. It'll be after the April vacation. She'll be back. You will be back by then. It's not going to be warm enough in March, probably.
Yeah, it'd have to be warm enough that we can all be
It has to
outside.
be- It'd have to be
Wait, so
middle
next
or
year
late
are we gonna-
April, probably.
hmm
Next year are we gonna learn about the volcanoes and
Yeah, next year we'll do the first half of the book. This year we're doing the second half of the book because we did the first half last year.
and then read all of it and be like,
Yes. All right. 13. You can throw a softball farther than you can throw a bowling ball.
2.
Gavin?
3. 1.
Well, sorry, that was confusing. No, it is actually 2. Isabel was correct. I just wanted to give you a chance to answer.
I was gonna say 2. I just kind of.
Yeah,
I
I
thought that
know
it
you
was
probably
wrong.
thought I was
Yeah.
saying she was wrong, but no, it is number 2. Can you tell us why it's number 2?
Cause the mass of the baseball is much smaller than a bowling ball because it weighs more.
Yeah, exactly. Yeah. All right, very good. So I think we're starting to get a grasp on these.
Isn't that right, Reed?
All right, so let's go on to page 140. And we have a couple more questions to answer. All right, so number 14 says stored energy that an object has because of its position is called, Isabel?
Potential.
Potential energy. Very good. So you can think of it has the potential to move, even though it hasn't moved yet. All right. Number 15. The ability to make something move is Azalea? C, mechanical energy. Good.
gave me the pencil. Use.
All right. Number 16. Energy that an object has because of its motion. Gavin, you want to take a...
Okay.
16.
My numbers.
16.
What is energy in motion?
Kinetic.
Good. Very good. All right. I think
Kinetic.
you guys must have learned
100
those
years later.
words before this class, huh? Did you guys learn potential and kinetic energy
No.
with
In
Mrs.
4th
Mayfield,
grade.
or-
I learned
Was
potential.
your science? No, that was, she wasn't.
Or was it Mrs. Fishman?
Mrs. Fishman.
Oh.
I didn't learn. We didn't learn potential energy
Oh.
then. We never.
Well, you guys picked it up very quickly then. That's good. All right.
17.
All right. Number 17. Speed is the blank in object travels in a specific time. Azalea.
B.
Isabel.
C. Distance.
Yes, very good. So speed is the distance an object travels
I was about to
in
say
a
A.
specific time.
And I was like, momentum.
Well, if you think, I think this is tricky too, the way that one is worded. But if you think about like miles per hour, right?
The speed was like a rate that like speed rate.
Well, yeah, it's how fast you can travel that specific distance in that amount of time. So when we're driving in a car, at least in the United States, we measure that by miles per hour. Whereas if you go to Europe, it's what, kilometers per hour?
Mhm.
Yes.
My brother Ben yesterday he yelled at my grandma for going 1 mile ahead of the speed limit.
Oh my goodness.
Just 1 mile. And he's like, Grandma, you went over the speed limit. And she was like, only 1 mile.
Yeah.
Well,
Especially on a long
Well,
and-
usually if you keep it within 5,
And
Yeah.
you're usually okay. You don't want to go any more than that, though.
we were behind a very slow car, so we were going way under the speed limit. And then Grandma needed to get to work fast because she needed to sort something out. So she had to go just like a tiny bit faster. And my brother was like, Grandma, you're over the speed limit.
Mhm.
And she was like,
Yeah.
there's a stinking car in front of me, so just let me alone.
Oh. All right.
What's the answer?
Now we're on to number 18.
I'm not here so you can see them.
Blank is speed in a given direction.
Hmm.
Azalea.
A.
A, velocity. Very good. All right.
So if you record velocity, would it have to have, in addition to the number, it would also have to have a word indicating the direction?
I think so. Yeah,
Yeah.
like you would. How you would say that? I mean, I guess
I've
you're
never
like
seen it written.
heading east.
Yeah.
Yeah.
I mean, I understand the
Mhm.
definition. I understand the definition, but I've never seen it written that way.
Yeah. Well, I think, yeah, this is, I mean, like we were talked about before,
Yeah.
this is one of those terms that is commonly misused,
Yes.
really, because we
Yeah.
generally use the word speed
Right.
for
Velocity.
anything like that.
Yeah.
Yeah.
It's a shame. I mean, I know that's true in grammar, but I don't like when it happens in science.
Yeah. Yeah.
It does happen.
I know. All right.
19.
19. A change in velocity during a period of time. Gavin?
Acceleration.
There you go.
Acceleration. Very good. So hopefully by the time Reed gets back, he'll know the difference
Yeah,
between
Reed.
acceleration
Your
and.
invisible self is right
Yeah,
there.
I
Better
often
be
thought
listening.
acceleration only meant it got faster.
Mhm.
I never thought of a decrease in speed as acceleration.
Yeah.
Oh, that's another.
Yeah, and I think
Common
it's one of
issue.
those things that way we're used to using that word. Yeah, interesting.
Yeah, like someone tells the car to accelerate over the radio. So it stops the car. Like in a car race. Accelerate the car.
Oh,
It
gotcha.
goes on break.
Yeah.
Oh boy.
Well, that's what I learned in science.
Yeah.
Why can race cars go so much faster than normal cars?
Because race
Because
cars
they're built-
are built to go faster than
But
regular
they wouldn't
cars.
work as normal cars because the rubber on the tires fall off every few seconds.
Not every 2
Well,
seconds.
there are actually laws about different things criteria a car has to fit in order to drive on the road. Some cars are not legal to drive on the road, which is why they actually have to be, like when they go to a racetrack, they actually have to be transported in a trailer, and then, because you can't drive those cars on the road. A lot of times they have very wide tires with no tread on them, and that would be extremely dangerous on the road. And then there's also, like, for cars that can go up to a certain speed, they have to have what's called a roll cage in it. So it's like beams that go around the frame of the car, so that if it was to flip over, which commonly happens in race cars, the person doesn't get crushed.
Do they have that? In race cars, do
Yes.
they have that?
Yeah,
They
I'm
have
pretty sure. I think it's anything over 400 horsepower.
Oh, really?
Something like
I
that.
don't know those specifications.
It might be maybe
So
a little
if I
bit more
hook-
than that,
If
but
I have a question, if I hook up 400 horses to a carriage and say, do I have like a Amish Lamborghini or something?
I don't think that's. I wonder how that horsepower that's not an
Yeah.
exact unit, really, is it? I mean,
well, it is a unit of measurement, but it's not really related to horses.
right. Right.
Yeah.
But what does horsepower mean?
The power.
It's how much. There's a lot of different things that go into it. My husband could tell you a lot better than I can. But it has to do with torque and speed and
I thought it started in the
How
beginning, it
quickly
just,
they
like, represented
accelerate.
how much horses.
Hmm?
In the beginning, cause they had carriages back then, they would sell it like how much horses, like it's 10 times stronger than a horse.
Hmm.
And
Well,
then
and that
that's
could very well
my
be where the
dad's
term
dad.
originally came from.
It started,
since,
yeah.
But I don't think they really have any way of measuring that related to horses. But all right, let's go on to the next one. All right, number 20. The mass and velocity of an object determine the object's length. Azalea. Momentum. Very good.
I was gonna say
Good. All right, number 21. Blank is a force that keeps an object from moving against other objects. Isabel.
that. Inertia? No, friction. B.
Friction. Yes, very good. All right.
The same thing.
And number 22. The pole of one object on another. Gavin, do you know what that one is?
I know 2 answers.
Gravity.
Gravity. Very good.
Yay.
How fast can a rat ride go?
I'm sorry, what?
How fast can a rat ride go?
What question is that? I'm not sure what a rat ride is.
You don't know
It's
what
like
a
a
rat
rat.
ride is?
No.
Amusement park? I don't know.
It's like a car, an older car. It's like an antique car, but it has it's like a handmade basically.
Oh. Well, I don't think. I mean, I know that like the Model Ts that they first came out. I don't think they went very fast. Like not like our cars that we have today. I'm not sure exactly how fast they could go, but
My Pop has a 1920 body and like a 1960 engine and a ton of other stuff. But I don't know how fast it goes.
Yeah.
And the back window is like this small.
Oh wow. Yeah. Well, and if you think about it, it was probably a good thing that they didn't make them go that fast because they didn't have the roads developed that we have now. Like, I'm sure you guys know if you went on a dirt road, you can't really drive as fast as you can on regular road.
Yeah.
Um,
Yeah, my granny went on a dirt road, and she was not that smart to go fast, and she got mud everywhere.
Yeah.
In her car.
And a lot of times, I mean, if it's, well, mud would be bad too, but if it's dry and there's lots of stones and stuff, you don't want all that kicked up into your engine,
Yeah.
you know, up in the wheel wells, and yeah, it can cause all kinds of problems.
Yeah.
What are you talking about?
Yes, sure.
Older, you know, the old cars like the Model T Ford that they had many, many years ago, and how fast they went as opposed to how fast our cars go today.
We are thinking about getting a truck for Dad,
Yeah.
but it's gonna be a used one, definitely. If we get one.
Yeah. Well, some of the older trucks I find are actually, some of them can be stronger and more reliable than some of the newer vehicles.
And they look better.
Yeah.
The newer ones just look so bad.
Yeah, because
Well, we do have, my husband has an old, I may have told you guys this, I don't remember, told one of my classes. He has a really old, I think it's like a maybe an 80s or 90s Ford pickup. But it has like I think it's a V8. That's like a really strong engine. And he has a plow on the front of it. It's actually not the prettiest looking truck, but he has a plow on the front of it, and he plows our driveway, and then he'll do a few of our neighbors and stuff when it snows.
But my
but
grandpa
this-
will drive, so he can hook up a plow to his
Mm-hmm.
so whenever it snows a lot, he'll go around like little on his street and just like plow out.
Yeah. Yeah, it was funny actually. Like, I don't know if it was last year or the year before. So in the village of Cooksaki, they have these big, heavy-duty plow trucks that come through and plow all the streets, and they're huge, big, giant trucks. And one of those trucks actually got stuck in the snow, and my husband pulled it out with his old Ford.
There you go.
So it was kind of funny.
What?
Yeah.
That's a very strong, tiny car.
Yes, very strong car, truck.
Powerful engine.
Yes. All right. So number 23. When does acceleration occur?
23.
When you have mass and force.
Are we gonna see that?
Well, they're related.
Oh,
it's related to mass and force, but
when there's the second law of motion happens.
so just in general, what does acceleration mean? When is acceleration happening? So if you're in a car and you're accelerating using the proper use of the word, what does that mean?
Acceleration. Action.
It can be when you're going faster. There's two other things that it can mean. So either
When
you
you speed up,
speed up.
when you go faster, and
Well, speeding up and going faster is the same
Speeding up
thing.
and stopping gradually.
Slowing down. And then there's actually one other thing that could be acceleration.
slowing down and running.
So if we look at the actual definition of acceleration, it says, oh, interesting. Well, I guess because it's a change, it's not a change in speed, it's a change in velocity during a period of time. And so let's look back to velocity. It means the distance an object moves over a given amount of time in a certain direction.
So it can change direction.
So if it changes direction, yes.
Changes directions or speeds up or slows down.
Mm-hmm.
Right?
So give you guys a minute to write
So you have
that
to have
down.
three things there. You have to have
Speeds up, slows down, or
changes direction.
Okay.
Put it up above. You're not gonna-
Which, like we talked about, I think the last class, a lot of times if you're going to change direction, you have to speed up or slow down because Otherwise, you're gonna crash your vehicle.
Unless you're in an action movie.
I mean, I guess if you're running, you could change direction and maintain the same speed.
You'd have to be
Yeah,
a
if
pretty
you're
good
Yeah,
athlete.
I know some football players.
They can do it.
Get some fancy footwork
Yeah,
going on
but
there.
even
one
they
of the
are
kids that-
not going.
Remember Rachel?
I mean, if
Pepper?
you're in your car and you keep the same amount of pressure on the gas pedal and you're going around a curve, I still think you'll slow down.
Yeah,
Curve, won't you?
probably.
My
I mean, I would
car
think. I mean, I know. I mean, if you're on foot or like on a motorcycle, for instance, it's easier because you can kind of lean
Yeah.
into the turn.
Yeah.
So maybe you can turn a little bit faster than you would in a
And
car.
on a
But
motorcycle, you still have to slow down because on races, when my Uncle Jake does it, when he puts his foot out, puts it on the ground, and then he slows down just a teensy bit, turns, puts his foot back up, and then goes.
I mean, I think if you maintain the same speed, you would lose control
yeah.
of the vehicle.
Yeah. I was always taught when my dad taught me how to drive. He said you always slow down going into the turn, and then you power out of the turn.
Yeah, that makes sense. Yeah.
Yes.
Remember Rachel Pepper?
I have heard of her. I never had her as a student, but
I did. So her little cousin, he does football with me and my uncle, and he well, in football they call it breaking ankles. So like he will go like this.
oh yeah, they go back and forth like this.
Yeah,
Jelly.
he go like side.
Yep. All right, let's go to the next one, which is probably the last one we're going to have time for today. So, see how much of you guys did the reading. What did Galileo discover about motion?
Galileo?
So we kind of talked about this discovery, but we didn't really talk about that Galileo was the one who discovered it.
Yeah.
Where was this in the book?
It's up to page
see here.
212 and
So that is on page 216. Talks about Galileo. So maybe we can I'll just read that to you guys. So medieval scientists believed that all things tend to slow down and come to a rest. Though these scientists made correct observations, their conclusions were wrong. Galilei, discovered that contrary to what the scientists of his day believed, a moving object does not come to rest unless an outside force acts on the object. Yes, you can go. So, that's one of the laws that we've studied. Which is, well, the opposite of it is up there. Gavin?
Objects that are not in motion tend to
I always thought that was the same as that was part of
stay
law
stopped.
number 1. That objects
Yeah.
I know.
at rest tend to stay at rest.
Yeah.
If it's in motion, tend to stay in motion.
Yeah, well, so the first law, it kind of covers both things, because it says an object tends to stay at the same velocity unless another force causes it to change.
But it says who continued his studies. But it says who continued.
Oh, well, that's, the next question.
Well, I guess if it's moving, gravity would be one of the things that would bring it to rest.
Yeah, that's a force that acts upon objects. And also friction.
Of course.
Remember we talked about the ball rolling down the hill?
Of course.
The grass and the dirt on that hill is causing friction against the ball. That's
Just
gonna,
the
and
air,
also
the air resistance.
Yep. Yeah. So there's quite a few forces at play actually.
yeah.
All right. So I think that's all we're gonna have time for today. So I would like for you guys for your homework to finish those questions there. There's just a few left. We got through most of them. So
140.
it would be page 140, number 25 through 29. So why don't you guys get out your agendas? You guys all have your agendas? I want you to get it out and write that down right now so you don't forget.
25 to
And I'll write it up here.
140. This book, both of these books need to go home because you might need this book to answer. Yes. Right, Azalea? You might need this book to answer the question. You need to look it up. Is any idea when there'll be a quiz or a test coming up?
Yes, there is going to be a